This video is part 1 of a mini-series on stationary states in quantum mechanics. You can find some links in the description below. In this video, I'm going to show that the probability density function that you get from a stationary state, which is a separable solution, is actually not dependent on time at all. There's no time dependence. So let's have a look at one of these separable solutions that we've actually been talking about in previous videos in the quantum mechanics playlist. So first of all, a separable solution or a stationary state takes this form. So I'm using capital psi of x and t to denote the wave function. And this wave function can be split apart into two parts. So there is a little psi, which just depends on x. And then there is an exponential factor, which is where the time dependence comes in. So we have a minus I et over h bar. So this is the time dependent part of the function, and this is the spatial part of the function. And this over here is a separable solution. And we're going to show that it's actually a stationary state because the time dependence actually cancels out when we calculate the probability density function. So let's go ahead and calculate the probability density function. The probability density function can be found using the wave function. What we have to do is we have to take the magnitude of the wave function and then we have to square it. So if we square the absolute, the magnitude of the wave function, what we're going to get is this over here. This is the square magnitude of the wave function. So that's the same as taking the complex conjugate of the wave function and multiplying it by the wave function. So psi star times psi. Now this is actually the same as this guy complex conjugated times this guy. So let's write that out in full using the definition up here. So what we're going to have is we're going to complex conjugate this part over here. It's going to be little psi star. And then we're going to have to complex conjugate this exponential. And there's only one I that appears over here, and that's this I. We're going to have to take that I and turn it into a plus I because it's a minus I. And we have to change the sign of all the imaginary components to do the complex conjugate. So that's going to give us e to the plus I e t over h bar. And then we just have to have this guy without the complex conjugate. So that's going to be little psi times e to the minus I e t over h bar. Now, we can actually move these guys around. That's commutativity, and you can actually move these guys around without any problem. And if you move them around, what you're going to get is little psi star times psi. So these guys are just the little ones. They depend on x. I've neglected to write the explicit dependence of x and t because we have that stated up here. And this is going to have e to the power of 0. Why is it 0? It's because using exponent laws, you can add these two guys together. And because these guys are the same, they just differ by a sign, they're actually going to add together to give 0. And e to the 0, that's just equal to 1. So this just turns into 1. And that means that we just get the absolute value of little psi, which just depends on x, all squared. And we're actually going to use this in the next few videos of this mini-series. The most important takeaway message from this video is that this guy over here, the probability density function, can be written just in terms of the spatial part of the wave function. Now this only holds for separable solutions. It only holds for these stationary states. If you don't have a separable solution, then these exponential factors won't cancel out. So these exponential factors only cancel out when the solution is of this form. And so we're actually going to use this in the next video when we deal with expectation values and stationary states. You can find all the other videos in the quantum mechanics playlist if you click over here.